Daniel Pfeifer. I'm from Munich. I work in the automotive industry. As I said, I'm from Munich. It's not that easy to find a job in Munich that has nothing to do with the automotive industry. But this topic here is about something completely different. This is something that I did in my free time. The talk is When Dependency Hell Freezes Over. So why I stand here today? It began around 2007 when people from the Boost community thought they wanted to have something more agile, turn Boost into something more agile that they can develop quicker and concentrate on library development rather than build system maintenance. So the idea was to move the Boost build system, or move Boost from the Boost build system to something that is more widely used. Okay, so back then CMake was rather new, and Git also was rather new. And the idea was to use CMake rather than Boost builds, to use Git rather than Subversion, to split Boost into individual repositories, one repository per library, for example, and then provide a tool that downloads the dependencies. When you just depend on one Boost library, you do not want to depend on the whole Boost. You just want to have a tool that downloads individual libraries that you actually depend on. Currently, there's a tool called BCP that can split Boost into such a subset, but the idea was to obsolete this. So work has begun. The Boost SVN was converted to Git and continuously pushed to Gitorious. And CMake list files appeared inside the Boost repository. My reaction back then, I was a student and had plenty of time, some hobby projects. I thought if Boost is going to use CMake in the future, then I should customize it myself with it. So I learned CMake, how it works, and I converted all my private projects to CMake. And to do that, I copied some of the CMake modules from Boost and evolved them. That were modules for unit testing and writing documentation, all that stuff. And I adapted them a little bit for my own needs and developed them further. But then the development of Ripple slowed down. Because the people involved did not continue working that hard, CMake list files in the end were orphaned and removed from the Boost SVN repository because nobody maintained them anymore, and they did not want to have something inside the Boost repository that is delivered which is not maintained and continuously tested, because there was no one who took over the maintenance of the CMake modules. And Eric Niebler wrote on the mailing list, I used this term CMake guy. We use a dedicated CMake guy that can concentrate on the development of those modules. So in about 2010, since I have evolved the Boost CMake modules, I customized myself with them. So I volunteered, hey, I could be such a CMake guy and maintain them. This is how I came in contact with Dave Abrahams, and then he convinced me to continue with him together to develop Ripple further. And so we worked together on Ripple, continuously evolved the CMake modules even more. However, we did not do it inside the Boost repository. We did it on a private clone. Yeah, and then in BoostCon 2012. Dave presented the current state of Ripple, like in all the years before. And at the same BoostCon, I also met Jens Weller, and he talked to me, hey, you worked together with Dave Abrahams, and I want to build such a conference like BoostCon in Germany. Why don't you give a talk? So now I'm here with a delay of 2 years, but finally I made it. So now I am here and give a talk about dependency management. So what is the actual problem that we want to solve? The question is, what is dependency hell? Maybe. Could that be dependency hell? What's your opinion? You know what this is? So this is, these are all the Boost libraries. And whenever one library includes a header file from another library, there is an arrow. Okay, and those are all the dependencies from Boost, so to say. If that is a valid interpretation of a dependency, but those are the includes. But whether that is dependency or hell, we need to have a clear definition what dependency hell actually is. So there are four possible ways of thinking of dependency hell. One is to have many dependencies. So when you have one executable that depends on many other libraries, right? That could be dependency hell. However, you think, what is the alternative to having many libraries? Is it better to implement everything from source yourself? Probably not, right? When you implement something like a browser or a computer game, you will have lots of functionality that you need to reuse that has been implemented already. So it's better to implement this. So I would not really say that many dependencies automatically means dependency hell. Because, yeah, is reinventing the wheel really a better alternative? Also, if you do that automatically, if you download the dependencies automatically, it's not a real issue. Another way is a long chain of dependencies. So that means you have an executable that depends on a library, which depends on a library, which again depends on a library, and so on. So it's very similar to many dependencies, but while many dependencies, if you draw the dependency graph, you will have a picture that is very wide, whereas when you have a long chain of dependencies, then the picture will be very deep, but the picture will be big in both cases. For example, if you try to build Clang, you go to the website of Clang, and you will find documentation. What are the individual steps that you have to perform to build Clang? So I copied that from the website. Well, if you copy line by line in your terminal, press enter, that's very tedious and error prone. So that could be hell. However, if you copy that into a script and execute it, you could actually check out and build Clang in a single step. So also would say that having many dependencies, whether that is in the horizontal or the vertical axis, is actually not a real issue if you automate that. Okay, but how could we automate it? If you go to Stack Overflow, we find a question like this. Here someone asked the question, how to automatically download C++ dependencies in a cross-platform way with CMake. And basically this is the workflow that I would like to support, right? You check out the repository, then you do some magic, or you execute a tool that does some magic, and afterwards you generate the project with CMake and build it like every other CMake project that you're used to. I certainly don't want to download the dependencies manually. So if you scroll down to the solutions, to the answers, we find here an answer from David Cole. Yeah, he was one of the maintainers of CMake. And what he gives here as a hint, as a solution, is not really attractive to C++ programmers. Right? So he says dependencies are evil. It's you should eliminate them. Don't depend on them. And this is probably what gets the most people angry. Prefer switching to Java to adding a C++ library dependency. And we see here the number of comments. About 18 people don't understand sarcasm. This is maybe a better hint here. Okay, the CMake provides a module called external project that can do that for you. You can automatically download dependencies. But really, downloading is not the real problem. Downloading is quite easy. Yeah? And you do not even have to do it in your build system. You can let the source control system do that for you. In SVN, for example, you can set an SVN external property that will download the dependent source code. In Git, there's a similar approach called git submodule. And in CMake, there's a command, if you'd want to do it inside the build system, there's a command called file download. And CMake can also extract archives, so you can build a completely cross-platform way to download archives and extract them. It also provides the way to execute processes. So you could provide a git command that does a checkout of something else. And that all has been implemented, okay? Inside the external project module from CMake, you can download and build dependencies during your build. So that's quite nice. Unless you have something like this. Okay, let's say we have some repository A that has a Git submodule or SVN repository, SVN external to repository B, which again has a SVN external to repository C, which then has an SVN external to repository A. And if you check that out, that's a nice way to fill up your hard disk. So this is also not working. So SVN external and Git submodules, they will not work. Right? They just do not solve that problem for us. But still, downloading is quite easy, right? It takes a little bit more logic, but not a lot more. And just do this, right? For each dependency, check out the repository into the root directory, unless it's already there, and do that recursively. Okay, so that means all your dependencies will form a flat hierarchy in your root repository, and then CMake will take care about the rest. You just run CMake, and yeah, each target links against some other targets, but it does not matter in what sequence you provide those targets. CMake can resolve them, and CMake can also handle circular dependencies. So that should not be a problem. Okay. So we go back to our list of what could dependency hell be. Circular dependencies, sometimes called spaghetti code. There's also an official term. It's called the big ball of mud architecture pattern. But those are architecture issues. Those are not build issues. Okay, it's a fact that architectures like this exist in the wild. Probably you know them. And if you have a build system or a dependency management system that cannot deal with them, you cannot use them. You cannot use such a system for your current project. So this does not really work. Okay, but we have seen it's still quite simple to get the source code. Now this one gets more hairy. Let's say we have a component B that depends on component D in some particular configuration, whether that may be a special version, particular release, or some build configuration, whether that may be debug or release, or static runtime, dynamic runtime, static build, dynamic build, whatever. And you have another library that also depends on D in a different configuration. Okay, that means those two configurations here from D, that means D1 and D2, they conflict with each other. Okay, and those conflicts here propagate, which means that B conflicts with C. And if you now have a component A that depends on both B and C, and those conflicts propagate, that means that A actually conflicts with A itself, so that's not a problem. So this is not solvable. You really have a problem here. So this is something that really gets us into dependency hell. And this was just a small example with four components, 4 projects. But really if you have something in the size of Boost, you want to have a system that automatically avoids those dependencies. You have to calculate something for you that you can then use. And this is something. It's not impossible to solve that, but it's certainly non-trivial. Okay. And here's another example that I want to show what's not working. Okay. This is the website of Lipcott, and you see here in the center of the website, the first thing that springs to your eye is this feature here. It has 0 dependencies. It's a library that has 0 dependencies, so they think they solve this problem of dependency hell for you if since this does not depend on anything else. Okay, and this is not the only library that shows that as a feature. Many libraries show sometimes they even call names. They sometimes even show as a feature our library does not depend on Boost. Or I also have seen a library that does not even need the STL. And I thought, how is that a cool feature? You probably have your own vector class. I don't. But the problem is that it's actually not true. If you go to the GitHub repository of libgit, you see here there's a folder called deps. And inside that folder, you find an HTTP parser, regex, and ZLip. And if you go to the ZLip folder, for example, what you find there is the source code of ZLip that has been copied into the repository. So now if you want to link libgit to your application statically, and your application also has to do something else with compressing, and it also needs to link against ZLip, then you have conflicting symbols. So this is actually not a solution at all. This is actually one of the source problems that gets us into dependency hell. So we certainly need another way out. Right? And I was thinking about that. What do we need? Is there a way out of dependency hell? So this is a little bit philosophical now. Because I was thinking about that, and also because I was thinking about a title for my presentation, and then I realized that getting out of dependency hell is actually not what we want. I thought, I don't go anywhere, okay? I'm perfect the way I am, my surroundings has to change. Okay? We want to stay here and turn dependency hell into something nice, right? Something that we would not describe as hell, okay? And then I thought, when would that happen? Okay. When dependency hell freezes over, then dependencies are cool, right? Not bad. Okay. Okay. So what we need, we would like to have a tool, or I prefer a library, because a library could be integrated into IDEs, for example, that determines a compatible set for our dependencies. Okay, so it should deal with version and configuration conflicts. It should avoid them, and it should make a decision what to download. It does not have to perform the download itself. Downloading is quite simple, but just making that decision for us what is actually required. Because that information is useful not only for actually building the source code, but for example, when we want to generate a text file with a list of all dependencies that we need. Or we want to generate a text file that contains all the licenses that is used by our software. Or whether we want to transitively collect whether all requirements have been satisfied, something like this. When we have the dependency information, what actually gets built into our software, we can use that in various ways. So, what would be the goals for a package manager? I use the term package manager because there was a talk on CPPCon. Boris Kolpakov gave a lightning talk about a C++ package manager, why we need one and what it would look like. I have a problem with that term, package here. Okay, I think it does not really, it's not the right term for what we need. Because what is a package? Something like this. What do we need packages for? I think a package is never what we need. We need something, and that something may be delivered to us in a package. Okay, but it's not the only way of delivering something. Maybe what we need is something that we already have. Then there's no need to get it in the first place. maybe someone else can give it to us, so there's no need to build it as a package. And even maybe what we need, maybe what we need comes in a package, and that package contains more than what we need. And to give a little bit more concrete examples, when we have a dependencies, for example, we want to build something that performs a download, so we use libcurl, for example, then in order to link against libcurl, we need the libcurl header files and the libraries, right? So this is what we call the development component of libcurl. And depending on the system, there are various ways to get that component. Maybe it's already installed. There's no need to download anything. Then on Arch Linux, for example, there's a package called curl, and it contains more than what we need. Not only the development component, but also the runtime component and the curl command line tool. So, but we can satisfy our requirements by downloading that package. On Ubuntu, there's a dedicated package for libcurl dev that contains just the development component. Okay, so there are various ways to get our dependencies resolved, and a package is not the only one. So I prefer the term dependency manager. I also have a problem with C++ here. I have nothing against C++, but in that context, C++ is too specific. Our source code, very often, our dependencies are not C++ dependencies. Many libraries are written in C, for example. So C/C++ maybe might be better, but even that is not explicit enough. Sometimes we have lex, yuck, mock. You have all kinds of sources that actually get compiled. Or sometimes it's not even source code. We want to compile documentation into a PDF. So this is not C++, certainly. But it's also something that is involved during our build. Okay. But still, I'm not sure about a better term. Software dependency manager maybe, or source dependency management, something like this. Just leave it. Goals for a C++ dependency manager. We certainly want to support pre-built libraries for various reasons. Using something that already has been built is maybe faster than building it ourselves, but also because it has less dependencies. Okay, for example, if you have a library that does parsing and provides us a C interface, and internally it uses Boost Spirit, then using that library and linking just against the C interface means we do not have a dependency against Boost Spirit. We do not have a transitive public dependency to Boost Spirit. But when we build that from source, of course, we also need the source code of Boost Spirit. So we want a way to determine dependencies without unnecessary downloads. So you might think, okay, that dependency metadata, where should it belong? We put it in the source code. And so you check out Git repositories transitively, and then you run the dependency solver, and you find out that for this particular configuration that was picked, some of the repositories that you checked out are actually not even used. This would be unnecessary. We do not want to, and therefore that means the dependency metadata cannot be inside the package and not only inside the repository. And we also would like to have integration with the system installer. On the Windows with MSI or on Linux with PackageKit, you can check whether a particular library is already installed. And otherwise, if it's not installed, maybe use it to install it. And you can also, on Windows, for example, you can determine where it is installed, because there's no such thing as a default install location. But once you know where it is installed on the system, you can directly use it if it is a compatible configuration, unless you cross-compile, for example. Then, of course, you can't. What we certainly do not want, we do not want to be forced to adapt our source code in any way. Okay, it is okay to add an additional file into our repository, but really changing the CPP files in order to be compatible with the dependency manager is something that is not going to work. Okay? We also do not want to be forced to adapt our build system in any way. I mean, it certainly makes sense to clean up some CMake scripts, but for example, what I want to avoid is something called, if you have in your CMake files, you have to call a function, name of the dependency manager, blah, blah, blah. For example, like rather than using add library, you have to use, I don't know, ripple add library. This is something that would create a too tight coupling with the dependency manager. This is something that I want to avoid. I would like to have a dependency manager completely separated from the build system. Okay. So how it could work. Let's say we add metadata to our source code repository. A file, maybe a JSON file or a YAML file. And then we could provide a tool that collects that metadata from all branches of the whole repository and, for example, compiles that into an XML file. And it would be nice if that is accessible through HTTP together with the XSL style sheet. This is, for example, the approach that Zero Install chooses. All the dependency feeds can actually browse with a web browser, and it shows the build information in your browser. So that is the advantage is then the dependency information that you provide to the user and the dependency information that you provide to an automatic dependency manager is identical. So it cannot be the case that you look at the documentation, it does something completely different what it actually does. So then the actual dependency manager should download that metadata through HTTP recursively, and then use Boolean satisfiability to find a valid configuration. And then do various things with that configuration, like downloading them and creating a source, creating a workspace or a solution for your IDE, or create a dependency file, and so on. So who knows what that means? Okay, do you know the Boolean satisfiability problem, how that works? Not really familiar, so let me explain. The Boolean satisfiability problem is given you have a Boolean expression, for example, A or B. The question is, can we assign values to A and B in such a way that the whole expression evaluates to true? In this case, yes, that would be possible. For example, we can assign A to true, B to false, for example, and then the whole expression here would evaluate to true. So we say this expression is satisfiable, right? Oh, come on. No. Sorry. I attended Scott's talk and I entered an animation here, and unfortunately it does not work. I'm really sorry for you. Okay, let me continue. The Boolean satisfiability problem. If you have such an expression here, A and not A, can we assign Boolean values to A and A, or to A, just A, that this evaluates to true? It's impossible. When we assign true, it's false, and if we assign false, it's also false. So this is something, this expression is unsatisfiable. So now, the question that mathematicians want to answer, is there an algorithm that can calculate whether an expression is satisfiable or not for a complex, for an individual complex Boolean expression? And the answer is, unfortunately, or we don't care, but for mathematicians it's unfortunate that there is no known algorithm. Okay? All possibilities have to be tried, and even if a possibility is found, we can say that it is satisfiable, and if we do not find a possibility that returns true, then we can, after we tried all of them, we can say there is no such solution. So this is an ongoing research topic. There's also a yearly competition. As programmers try to come up with programs that solve dependency problems in the shortest amount of time. But for our use case, the state of the art is advanced enough. Because we do not only want to have the statement whether it's satisfiable or not, we actually care about the solution that has been found. So this is not a problem for us. And for us, it's fast enough, because most of the time our problems are satisfiable and we just want to find a solution. So what is the algorithm that is state of the art that can be used to solve such problems? First of all, the expression is normalized into clauses that are ANDed together. Those are the clauses here, right? With parentheses, those are the clauses. And internally, the clauses are ORed together literals. So this, for example, is a clause. This is a literal. And then a literal may be a variable that is potentially negated. Okay? So the variables would be ABC. The literals would be those, and the clauses would be those. Okay. And then the next observation is, if for one clause all literals but one are okay. Let me start like this. The whole expression is true if each individual clause is true. Okay. And for a clause to be true, at least one literal must be true. So if all literals except one are false, we know that the remaining literal can be set to true in order to make that clause evaluate to true. And if all literals but one are false, we say the clause is unit. Okay? So for example here, in this example, this clause here is unit. It contains only one literal, so that must be set to true. And the literal is set to true by setting the variable a to false. Okay? And if we know that a is false, this clause here becomes unit. We need to set this literal here to true, and we set the literal to true by setting the variable c to false. And now if a and c are false, this clause here becomes unit, so we need to set the remaining literal b to true, and then we found a solution. It is satisfiable. Okay, so that is the algorithm that we can use to solve the satisfiability problem. In this example here, it was possible just by unit propagation to find a solution. Usually, it goes like this: you find a variable that is not yet set, and you set it, you assign it a value, either true or false. Then you perform unit propagation, and you repeat that until all variables are decided. If you make a decision and you do unit propagation and it comes to a conflict, for example, that two clauses become units, and one of the clauses expects a particular literal to be set to false, and another one expects to set the identical literal to true, that is a conflict. That does not work. So we need to backtrack in that case, and we need to learn that the decision that we made was wrong. So we learn, that this decision that we made actually leads to a conflict. So we store that in our learned clauses and continue backtracking until we found, until all variables are decided. Then we found a solution. Or we have a conflict at top level, in which case there is no solution. Okay. So how can we use the satisfiability problem for dependency solving? Well, the approach would be the following. We use a so-called database. It's not what we usually think about databases. It's just a vector of implementations. Okay? And each implementation represents one possible way of retrieving one component from a particular project. And each implementation can have dependencies and conflict in the form of specifications. So it's not the case that one package depends on another package, but it's one implementation has a requirement, and that requirement can be satisfied by one or more other implementations. Okay? And same with conflicts. They're also in the form of specifications. And now the way we turn this dependency information into a satisfiability problem is the following. When you have a dependency, for example, the implementation A requires the specification B, and the specification B is provided by the implementations B1, B2, and B3, then we would enter such a clause here into our dependency expression. Okay. In case of a conflict, for example, the implementation A conflicts with B, which is provided by B1, B2, B3, we would enter 3 clauses into the expression. Okay, so we sorry. Is
that a minus or no minus before the B1, B2, B3? Which one of them? The first one, right?
Oh, this is the first one. Yes. Sorry. So this is a typo here. They all need to be negated. So this means either of them, one of them must be true in this case here. Either B1 is installed, or B2 is installed, or B3 is installed, or A cannot be installed. So this is the way this dependency is expressed. And in here, it means either, so a conflict means either this is not installed or this is not installed. They cannot be both installed. And here those are typos. It also should mean this is not installed or this is not installed, and this is not installed or this is not installed. Thanks. We also have implicit conflicts. So we first enter all the dependencies and conflicts that are listed explicitly in our metadata, but we also add implicit conflicts. For example, when we have different implementations from the same project in different versions or different configurations, they should conflict with each other. So we do not want to have the case that we use the developer components together with a library in a different version. So this will lead to problems. Implementation that provide the same components. For example, if you have a way, if you have, for example, a package that contains just the development components, and you can also download an archive from somewhere that contains all components, including the development components, that should also create a conflict. And pre-built implementations conflict with their dependencies when they are built from source. So by that, we want to avoid that we build something from source that is then used by something else which is already built. This is leading to problems. So when something is built from source, it propagates to the top. Everything above also needs to be built from source. Okay? It's okay to have pre-built dependencies below, but not on the top. So the final workflow would be this. We perform the manual steps. We clone one or more projects into our workspace. And then we run a tool that retrieves the dependencies, and in the end, we just run CMake and build the project. Internally, the tool would do the following. It first scans the metadata from those projects. It only scans the current branches, only that what we are going to build. And then it fetches the dependency metadata from the dependencies recursively via HTTP, for example. It collects all that metadata, turns it into a satisfiability problem, solves that satisfiability problem. So what we get is, for all implementations that we collected, all possible ways to retrieve something, we have the information whether that should be used or not. So this Boolean information. So what I describe here as a solution is exactly the implementations that have a value of true set. Okay, and this information can be used for various things. First of all, we should save it for reproducibility. We want to know which configuration actually has been built. Then we can retrieve the actual source code for those implementations or install the binary packages. And then we can generate a top-level CMake lists. For example, it could contain add subdirectory for each dependency that is built from source, or find package for each dependency that is used in a compiled way. Yeah. Should work. Yeah. So, thanks. That is I think the approach of a dependency manager, how it could work. So do you have questions? Yeah.
It sounds like the satisfiability problem that you have is basically the SAT3 problem that's proven to be NP-complete. So how does it avoid taking a non-polynomial time on that?
Sorry, what was the question? Yeah.
It sounds like the problem that you have, the SAT problem, is the SAT3 problem that it's basically proven to be NP-complete. Yes. How do you avoid taking non-polynomial time for complex projects?
The last sentence again.
NP-complete problems have no polynomial solution, which means that the best thing you can do is do the non-polynomial solution and see if it fits, which means that you might take, for a project of 50 subcomponents, you might take a few petabytes of memory and infinite time. How do you avoid that?
I mean, it's not our of course, if you have problems of that size, but we usually don't have problems of that size. We usually don't have that many conflicts. So a project has a couple of dependencies, usually not many conflicts, and also not many releases that are actively maintained. And if the dependency information, if the metadata is updated accordingly, for example, that 3 releases of a library are maintained, then you will not have big problems that leads to long calculation times. So satisfiability solvers are also used in, for example, in the dependency manager of SUSE and Red Hat, and by migrating from their own from the old solver to a SAT solver, actually improved the performance considerably.
Okay.
Can you go back one slide, please? Wouldn't it be better to integrate the running of the tool directly in CMake?
Yes, certainly. This is what I said. That's the reason why I would prefer a library for that approach rather than a tool. In the first step, I mean, we can provide a tool that does that in order to prove that it's possible. But in the end, it would be nice that logic could be implemented directly in CMake or in some other IDE.
And the second question, what's the difference to other package management systems like apt-get or whatever exists? They also have the dependency problem and they solve it. So what's the difference with the new, why would we need a new package management system?
I mean, something like apt-get is, first of all, not cross-platform. We want to have something that works on Windows as well, and not something that works as an alien on Windows, but really integrates with the system. And therefore, something like support of MSI packages, in my opinion, should be a requirement.
How would that be supported?
I mean, MSI provides an API in order. that you can use to check whether a package is installed or not. You have to give it a UUID that identifies a package and another UUID that identifies the component of that package. And then you can retrieve information whether the package is installed, where it is installed, etc. And there's also a way to install packages. You have to give it the URL to an MSI package and some installation options, and then you can actually install packages directly on the system.
Okay.
So how do you find an optimal solution with your set solver? If I understand correctly, it's it is solvable or it is not. So if you have, for example, 3 components that are all available as source and as binary, and a perfect dependency solver would choose the binaries to reduce compile time.
Right. So if we go back to the algorithm, here the algorithm is we find an undefined variable. And when we find, and this is exactly where we can make such an influence. When we design the variable, we would prefer pre-built packages. So we would prefer a variable of a pre-built package and assign that to true. And only if that fails, we use another value. And then we can influence various ways. We can, for example, I would implement it that way. First of all, prefer the packages from the system package manager. If that fails, search for packages that are hosted somewhere that you can install as an archive. And if that fails, as a fallback, compiling from source should always work. But even that is sometimes possible that it's not available. For example, companies could use that for closed source applications. God forbid, but it certainly would be possible that that binary packages for some implementations are available, but source code is not. But this is the place where such decisions can be made.
Okay, so I heard that you want to have it like cross-platform for Windows and Linux. And I was using a tool in Windows. I'm not very professional at that, but it's called Nougat. It's a quite new dependency manager, I think, for Windows. I think the Visual Studio 2013 used it as a default. Can you elaborate on that? Did you try it? If it's okay, the Nougat.
As far as I know, Nougat does not satisfy all the requirements that are listed. So first of all, I think it only works for Windows, and even on Windows, it only works inside Visual Studio. The source code is not available. It does not support. I don't know whether it supports both pre-built and libraries from source. So many of the requirements that I would have to such a system are not solved by Nougat.
Okay.
I have one comment to Nougat. It works on Linux, but it does not solve all your requirements. That's Is it possible with your solution to have a scenario like this? I'm a developer on a developer machine that works on 2 different components. So I may decide, okay, I want to build those from source because, for example, I check them out or set a flag or something like this. Whereas the build machine usually always fetches the binaries or something like this.
Certainly would be possible, yeah.
Yeah, okay. Would be possible means it's not in there, or is there already something, or is it just a possibility that this can be solved, this problem?
Most of the talk is a possibility.
Okay.
Okay.
I have a question that I found by myself. Where have all the REPL devs gone?
Yeah. REPL developers, most of them have gone to Apple, some to Google, some to other companies. The main problem is that building something like this takes a lot of time, and and all the developers are not paid to work on REPL. And it's even worse, the developers that have been working on REPL are actually paid to do something else. So they're actually paid not to develop REPL any further. That's sad, but the same is true for me. I just don't find the time to invest. Don't find the time that I would like to invest to solve that problem.
Do you have the answer to the other two example questions?
No.
That's a serious question, by the way.
Okay. So,
Okay, so the first question would be, what does RIPL stand for?
okay. You want to have answers for the example questions, okay? What does RIPL stand for? That's a long story. Do you know what Boost stands for?
To be quite honest, no.
Okay. It has been explained in a talk by Dave Abrahams. So Boost. That was about when the first standard of C++ was published. Around that time, there was another famous programming language called Java, and there was quite a hype about that programming language because it's in many ways so much better than C++. And Dave, for example, said, okay, this language has such a large libraries, standard libraries, and what does C++ have? An IO stream library. That was quite sad. And the idea was, and in Java, it was also funny to have this analogy of coffee and the programming language. So the idea was, what is stronger than coffee? And they said, alcohol is stronger than coffee. So that's where the name Boost comes from, and which was later changed to Boost. So the idea of Boost is stronger than Java. And RIPL just happens to be some cheap form of Boost.
Okay, and the other question I would actually like to contribute. So, how can I?
On the title page, you find my email. I think the best way would just to contact me.
Okay, thanks.
Or just talk to me after the talk.
So, and right now, where are we right now? And based on all the study you did so far about all the alternative, in your opinion, if I am deep in the dependency hell, and I need to solve it in next weeks, to improve it, actually, that's exactly what I have to do. What is the best tools, or do you have any clue to help us in this direction?
I think, in my opinion, really, I would love to have a solution for this. I mean, it depends. What exactly do you mean by dependency hell? Do you have a spaghetti architecture, or do you really want to download your dependencies?
No, we have all the source code is downloaded at once. It's about 6 gigabytes, so everything inside, including Qt and Boost. The problem is building. It's an old customized version of QMake 3, and it takes like 5 minutes, and we don't know how to get rid of that because that's the problem number one in C++, in my opinion. When you include a header file from one library, you have in Cascade to include everything else, and we have 220 projects, and everybody comes with its own idea, but how to solve that? And yes. I would be curious. You here, how do you solve dependencies management, all the headers in Cascade? How do you solve that approach on such a large scale?
I think the first important thing is certainly the architecture. Change the architecture in a way that dependencies are reduced. And you can do that, for example, include dependencies can be solved by introducing compiler firewalls, pimples, or something like this. And the same approach can be used on all scales. You can use the same approach also for libraries, abstract dependencies, right? That you provide a library that has some private dependencies, and those dependencies do not propagate any further because they are not used in the public interface. So this is a way how you can reduce the dependencies, that each individual component only has a small set of dependencies that it needs to link against, and then you need to combine that with binary releases. So you compile one component and you made it somehow accessible for the other parts. I think this is the best approach. Well, there's certainly not something that you can solve in about 2 weeks. It's more effort.
One question. So you said that this whole thing does not depend on the kind of build system really, but it's separate from that.
Yes.
So I made the experience that sometimes it actually depends on your build settings, for example. Like if you have dependencies that you want to build from source, then maybe this breaks if you try to use a newer version of the compiler, or if you use, for example, binary libraries, which you link against, this may break if, I don't know, you decide to dynamically link your runtime library instead of statically,
sure,
and this kind of stuff. So
okay,
sometimes it really depends also on how you build your project and
of course
how you solve that.
So it can depend on your build settings. But what I want is, what I wanted to have, I want to have something that does not depend on the build system. For example, I do not want to have a solution that only works with CMake. It should also work just with Visual Studio or some other build system generator. It should not be tied to one particular tool, but certainly your build settings, they are not independent. There's no way to get around that.
Yeah, that's the point. So I think the only way would be to integrate it probably directly into CMake, because otherwise you will not be able to represent this in any way, I think.
Yes. Probably, yes. Mm-hmm.
Quick question, which tool do you use to draw all the dependencies between the modules? We have thousands and thousands of files.
What I did, the tool was, so I created a dot file, but then in order to visualize it, I did not use the dot tool, but some other tool that comes with GraphViz. I tried a couple of them, and the picture that is generated with dot is so wide it does not fit on the slide. So I tried a couple of them and used the one that fits best. I think it was 2π or something like that.
So I have a suggestion. So in our company, we also have many modules, mostly pre-built, and we started to use the dependency inversion pattern, and this helped us to get rid of some of the dependencies. So the tree just shrunk, and yes, it's not that warm anymore.
This is exactly by what I said when what I meant when I said you have to make influences on the architecture. Solve that on an architecture level. Yeah.
And another question: what license comes or is Ripple developed with?
I think most of that, as I said, most of that exists as an idea. I also have prototype and example code where I try to solve that. But I'm really open. What I want to have is a solution, and a solution that everybody can use regardless of license restrictions. So I'm happy with Boost license, MIT, BSD, whatever. Yeah.
Any further questions?
I don't think it's a good idea to make subdirectories directly in the project. Maybe you want different variants, different branches, and compile them all, and they may depend largely on the same libraries. So it would be better to have a system folder where everything is installed and track the versions and configurations that are placed there, and in the project only link to them.
Yeah, I'm not sure I agree. The thing is, that's usually what people try. People try to build both the static runtime, both the static library and the dynamic library inside the same project. And I strongly recommend against that, because CMake has a standard way of choosing whether all libraries should be built per default static or shared. And if you explicitly add a shared library or a static library, you actually disable that ability, and you actually constrain what your user, actually constrain the way your users are used to using CMake. So I really strongly recommend against that, and I would rather trust the CMake defaults and trust the way users are used to tweaking with those results. I also strongly recommend against setting compile flags in your CMake projects. For example, when you have something like this, you want your library to be built with all warnings enabled and treating as errors. And then you constrain the way your users build your library. It's okay if you want to build it like this, but you should not force anyone else to use it like this, because those settings can propagate and then conflict with some other libraries.
Oh, well, for some version systems, it's maybe not so optimum if you have the external dependencies and the your sources in one folder hierarchy. So I personally prefer it to put it something where you can see this is external and this is from.
Sure.
So maybe it fits for CMake, and I don't want to put it much away, but in a way that I can see what comes from what kind of source control or
Yes.
from what.
As long as it is outside of your actually library, because if all libraries pull their dependencies inside, you will have a problem when you have circular dependencies. But as long as you put them all to some known place, then it should work. Where that known place is, whether it's really the root or somewhere else,
well, maybe we just have a different view of the root directory. So if what I understand the root is the root of my project, and if you say my project,
right,
my project is one
completely
level
agree, yes.
different. Yeah, when we are on the same level.
Yes.
And I want to mention that if a project uses this tool, it's just another dependency for that project. So we have to solve another dependency problem, and maybe it's a good idea to provide standard scripts that start downloading and installing this tool. So a casual customer has only to run one script. So instead of providing a list of dependencies, what he has to install, just one script and say, okay, start this, and project should build.
Probably yes. And that's again the reason why I think something like this should be implemented as a library, because then it can be integrated into something else. And it's also the reason why I want to have it separated and not coupled to a particular build system, because if you have it coupled to a build system, then you exactly lose that flexibility. Okay. Because if I couple it to a build system, I introduce a dependency to that build system. And if I have it separated, then I can leave it open how it is integrated somewhere else. Yeah. Okay, thanks.